Hey there, now we're about to start Unit 7, which is about Hess's Law. Basically, Hess's Law is a concept that talks about reactions that happen in several steps. We may call them mechanisms. I will define along the way how the whole concept works, but let's start by an example. We have grapes on the left-hand side, and we have the finished product on the right-hand side, the wine. Obviously, it takes a very long time before we go from the fruit itself to the drink. There's many steps in between, and those steps can be very slow. It can take a very long time. So Hess's law basically analyzes the whole process as a whole, not only the individual steps. So it will do both. Now, Hess's law will sometimes talk about processes like this one that are very, very slow or very long, and sometimes it's going to be processes that are too fast for us to really observe. It appears as if the process is done in one step, for example, an explosion, but in reality, it's really a chain of reaction that cause what we actually observe as one step. So that's what Hess's law is all about. It's the study of those mechanisms. So if I may look or show you a first example, we have here NO, two molecules of NO that react together, as well as one molecule of oxygen. So all this reacts together in order to form two molecules of NO2. Again, to the naked eye or to the observer, this may look as if this happens in one step, but actually it happens in two steps. So we have the first step here. The two molecules of NO react together, rearrange themselves to form N2O2. Now this product becomes the reactant in a second step, and this N2O2 then reacts with the oxygen gas to form the final product, the NO2 gas. That substance that we have in between, that is being reused in the second step, is called an intermediate substance. Now if we look at the different steps, we can actually add them up and obtain the overall reaction that we observed before. I just want to go back for a second. So what we want to do here is take this step and add it with this step, and what we get is this overall reaction. So I'll show you over here how it works. So I have the first step, the 2NO2, that rearrange to form the intermediate, and then the intermediate reacts with oxygen to form the final product, right? So the overall reaction would go from here to here, as if it was one step. Now, if we add up those two equations, what we obtain, so here they've just rewritten everything, right? They've rewritten all three reactants on this side and the two products on this side, as if we're doing a mathematical sum. And they canceled out what appears on both sides in the same quantity. So I have one N2O2 and another one N2O2 on this side, because obviously I had the intermediate here and here, right? So they cancel out. And what am I left with? I'm left with this equation here, which is basically what I had earlier over here as what I actually observed. So I can take the separate steps, first step here, second step here, add them up and obtain the final or observable reaction. Now, if we look at a graph, how do we represent this? Well, a mechanism has several steps, right? So it has step number one here, so the graph that's in green, for example. I have substance A that reacts to become substance B. It has its own activation energy, it has its own delta H. But that's not the only step of the system. So my substance B, that was the product of the first reaction, becomes the reactant of the second reaction. So it's being reused into a second step, a second reaction, which has its own activation energy and its own delta H. And that substance C, the product of the second step, is now reused as a reactant for the third step. And again, I have a new product. I have an activation energy for the third step, a delta H for the third step. That substance D, which was the product of the blue reaction, would then be reused as a reactant for the last step to get the final product, which is letter E or substance E. And again, that fourth step has its own activation energy, its own delta H as well. So to find the delta H, the energy involved in the whole process, what do we have to do? Well, it's written here underneath. we have to add up the different individual delta H's. So this one plus this one plus this one plus this one will give me the amount of enthalpy involved for the whole process. So the total enthalpy change for the whole process or reaction or mechanism, whatever you want to call it. So that's what Hess's law is all about. That's what it explains. Now here you see that some of these delta H's are negative, exothermic. This one is exo, this one is endo, this one is exo. And this here will reflect that. Since all three are exothermic, and one of them only is endo and very little endothermic, it absorbs very little energy, the overall should be exothermic. So this will really reflect the sum of all four. Another point I want to make is we'll talk sometimes about the limiting step. Which one would limit the whole reaction or would make the whole process slow down? Well, if you think about group work, if there are 4 people working in the group, and so 1, 2, 3, 4, and you're each in charge of a step of a process. Let's say you're writing a lab report. Well, the person that's the slowest is really limiting the whole work or the whole process, the whole writing of the lab report. So you're always as fast as the slowest member of your team. So which one here would be the slowest step or the limiting step? Well, it should be the one with the highest activation energy. It's much harder to go over this hill over here. So the second hill over here is much more difficult to pass than any of these. So this one would be the limiting step. That's step number 2 will be the rate or the speed limiting step because it's the slowest one, it's the hardest to pass. So why or when do we use Hess's law? I kind of talked about it before. For very slow reactions, like the aging of wine in wooden barrels, certain reactions are so slow we can't actually observe the changes. The changes are made so gradually that we don't even know where one starts and the other one finishes. I'm talking about the different steps here. So let's say there's 5 steps to the aging of the wine. Well, those 5 steps may be so slow that you don't know where one starts and the other one ends. And because of that, we see the whole process as a whole, as if it was one big reaction when actually there are different steps to it. So we're going to use Hess's law for very slow reactions or for the total opposite, very violent reactions, like the combustion of magnesium. So something that happens so fast that, again, it looks as if it's happening in one step, but it's really not in reality. Or other types of reaction, very complex, where we know there are several steps. And because it is so complex, we need to really detail every step of the whole process, and we call those mechanisms. So that's when we're going to see Hess's law being used.